Hello and welcome back to Dr. Logic Awkwardly Does Logic in a new version of Zoom, but don't worry, I think I know where the whiteboard is. In the previous video, I gave you a very brief sketch of what we're going to do with the canonical models method. In this video, I want to give sort of a roadmap through it so that as we go through each portion, you have a sense of why we are doing it, what it's for, and how everything fits together. So let's see if I do know where the whiteboard is. I think. New whiteboard. There we go. It's loading. Excellent. My goodness, this is completely different. Let's hope it works the way that I'm used to. The first thing that I want to do is talk about the notion of a system. So whoa, that is not how we want to be writing. Let's try this. No. There we go. A logical system. Now, we have defined these previously on the basis of axiomatic bases. So you've got a set of axioms, a set of rules of inference, and then this generates a set of theorems. So that was one way of defining a logical system, which is taking the axiomatic basis plus rules of inference. Now, that was very nice because it gave us a very kind of concise way of identifying individual systems because most of the ones we've looked at have had a finite axiomatic basis. However, we have seen two systems that give rise to the same set of theorems, namely the two different axiomatic bases for S5. So another way of thinking about a logical system is to just gloss over how it's generated. So don't pay attention to the precise set of axioms you started with, and just look at the set of theorems generated. So this is what we're going to be doing now. So like when we talk about S5, we mean whichever axiomatic basis you want, all of the theorems generated from that. Because we can show that different bases are equivalent, then it doesn't really matter which one we start from. So from now on, when I talk about a logical system, I'm going to be talking about the set of theorems that are generated. Now, just a reminder to get our statement of completeness. So a logical system S is complete with respect to some semantics, in our case, a class of Kripke frames C, and we'll superscript it with an S because we're talking about system S, if for all phi, if phi is valid on the class of frames, then you can derive it in the system S. Now, as I said, our route to proving this will be contrapositive. So if we have something that is not a theorem, then it will not be valid on the class of frames. Now, what this means is that there is some frame f of S in the class of frames and some model M of S on that frame where I'm going to run out of room. There is a world W where phi is false. So we go from being a non-theorem to being false in at least one world on one model in one frame in the class of frames. So that is the process that we are going to go. Now the question is, can I figure out how to make a new whiteboard page on this new system? Let's try this. Add page. Oh, magic. The wonders of modern technology. So we're going to pick an arbitrary non-theorem and then show that we can show that it is false in some world on some model in some frame in some frame in the class of frames. That is the general picture. So what we're going to give, the canonical models method, gives us a general way of generating the model that falsifies the non-theorem. So a canonical model is going to be one where for every non-theorem, so the canonical model for system S, where every non-theorem of S is false in at least one world in the model. This means we need to define what the model is. This means we need to define what are the worlds in the canonical model. When are two worlds, so what are the worlds in the canonical model? When are two worlds in the canonical model related? When do they see each other? And the valuation, what atoms are true at which worlds? This is what we need to define. And then once we have constructed this model, we will then show that it has a particular characteristic, which is what allows us to do all of the steps that we need to do for completeness. But I will say a bit more about what that is once we get closer into actually constructing the model. These are going to be the things that we're going to be focusing on in the coming videos. Our roadmap is, first we will define what the worlds are, then we will define how they are related to each other, then we will define the valuation, and then we will show that for particular types of systems, this model has a specific property which allows us to prove completeness. So there we are. I hope this gives you a sense of where we're going and what we're going to be doing. And I look forward to having you back again next time, where we will begin to define what it is to be a world in the canonical model. Until then, take care. Cheers.